Hello everyone and welcome to this lecture. In this lecture, we will start a new topic, and this new topic is algebraic connectivity, a very famous topic. Okay. In order to define what algebraic connectivity, we have to go back to our famous matrix, and this matrix is Laplacian matrix. Okay. So what was the Laplacian matrix? So remember, if we have a graph Z, okay, the Laplacian matrix is nothing but, we denote it by LG, okay, was nothing but degree matrix minus our adjacency matrix, and we have seen many beautiful properties of this Laplacian matrix. The one thing that was very crucial is this matrix is actually, so I will denote it by simply by L, okay, simply by L, is positive semi-definite matrix. That means all the eigenvalues of L are always non-negative. Okay, and there was one more important thing, is that 0 will always be an eigenvalue. And why it is so? If you see the structure of L, okay, on the diagonal there are degrees, and off diagonal are -1 whenever there is two vertices I and J have an edge between them, then it will be -1, otherwise 0. So if you add all the entries of a row, it will give you 0. Okay, so that means all one vector is an eigenvector corresponding to 0 eigenvalue. Okay, now what about the second smallest eigenvalue? The first smallest eigenvalue is by default 0. What about the second smallest eigenvalue? Let us denote the second smallest eigenvalue by mu. Okay, so second smallest eigenvalue of L. Okay, remember, if this mu is also 0, that means what? The graph is disconnected. G is disconnected. And why it happens? We have already proven that the multiplicity of 0 as an eigenvalue tells that the same number of connected components are there. Okay, so if the multiplicity is k, that means there are k connected components are there. So if mu is also 0, that means there are more than one connected component as the graph is disconnected. And by the way, what about the mu of kn? Okay, what about for suppose complete graph on n vertices, complete graph, what will be its mu? If you check this, the mu is nothing but n, the best possible. Okay, so in a way, this mu tells how well connected a graph is, and it was introduced by Fiedler. Okay, and due to it, the eigenvector or eigenvector corresponding to mu, okay, is known as Fiedler vector. Okay, so Fiedler vector is actually, so let me now write it. Fiedler vector, an eigenvector corresponding to mu. Okay, corresponding to mu. Okay, we will see very beautiful results just by looking at mu, okay, in this lecture. Okay, but there is one more important thing. Okay, I mean, if you see that this, suppose x is a Fiedler vector, okay, this has to be orthogonal to all one vector. This is coming from just a spectral theorem or just a Rayleigh quotient. Okay, because this all the eigenvector, because it's a symmetry matrix, so we can always take the eigenvectors to be orthogonal. One is already there, so x is has to be perpendicular to or orthogonal to 1. That means in x there will be some positive entries, there will be some negative entries, and maybe some 0 entries. Okay, so now let us move forward for one beautiful theorem based on the structure of x. Okay, so suppose, so I told you, right, there will be some positive entries, some negative entries, some 0 entries. So let me define two vertex at using x. Okay, so using x. Okay, so suppose I denote a vertex at v plus. Now I'm talking about the vertex of the graph G. Is actually all the indices, okay, all the indices such that, or all the vertex I such that the corresponding entry in your Fiedler vector is positive or greater than, so such that xi is greater or equal to 0. Okay, and similarly, suppose v minus is set of vertices I where all these I are less or equal to 0. Okay, so these are basically I think very simple notations and definitions of this v plus and v minus. And by the way, both of these will be, suppose if graph is connected, if the graph is connected, then the both has to be non-empty. Okay, so if G is connected, if G is, let me write, is connected, then V plus and V minus both are non-empty. Why it is so? Why it is so? Non-empty. Yeah, it's due to this. It's due to this fact. Okay, very good. So now let me introduce or give a very nice a theorem on just structure of basically the Fiedler vector. Okay, so let G be a connected graph. Then the theorem is V plus, and I will write similarly V minus similarly V minus. Okay, so this is a vertex set, right? This is a subset of a vertex set. Okay, induced rather than, so maybe I will this spelling, induce a connected subgraph. Okay, so basically what you do, okay, if you pick all the vertices in V plus, okay, and think about the induced subgraph on it, this will be connected subgraph. This will be connected. Similarly, if you pick vertices in V minus and see the induced subgraph on V minus, this will be again connected subgraph. Okay, so how to prove this? How to prove this beautiful fact? Okay, so but before that I need theorem. Okay, theorem. This is theorem. Okay, I need to prove. Actually, I have to make use of a very small result, very crisp result. Okay, so let me first write that result, and then we will head towards proving this beautiful theorem. Okay, so the result is this. Okay, so I need let me call it lemma actually, because I will be using it for proving this nice result. Okay, so suppose B is a symmetry, positive semi-definite. Suppose let B be positive semi-definite matrix. Okay, of order n cross n, of order n cross n. Okay, then our claim is then X transpose for any vector X. Okay, so maybe I will for any vector X, for any vector X. Okay, X transpose Bx equal to 0 if and only if Bx is equal to 0. How to prove this? This is very simple one. So we know that let us first prove it. Okay, we know that if B is positive semi-definite, as B is positive semi-definite matrix, that means there exists a matrix C. Such that B equal to C transpose C. This also we have seen many times. Okay, now you see that what will be this? If you do X transpose Bx, okay, so this is nothing but X transpose C transpose Cx, right? This is this. So that means this is nothing but this you can write actually as Cx transpose Cx. Now this is X transpose Bx 0 implies that C transpose X is actually 0, right? This is coming from here. So now, so Cx is 0. That means what? If you do this, this further implies that C transpose Cs is equal to 0. Okay, so we have actually proven that one part, that this will imply that Bx is equal to 0, and the converse part is actually very obvious. So converse part is obvious. So if Bx is equal to 0, that means this is X transpose Bx. So converse part is straightforward. Okay, converse is obvious. Okay, very good. Very good. So we will make use of this result to prove our the main theorem for today. Okay, so the theorem is V plus induce a connected subgraph. Remember what was V plus? V plus were all the vertices in G such that corresponding entries in your Fiedler vectors are non-negative. Okay, so let us prove the proof of theorem. So let me write it here. The proof of the theorem. Okay, very good. Okay, since V plus is non-negative, okay, so V plus is non-negative. We have seen that because X Fiedler vector has to be perpendicular to 1. So it's a non-empty. Okay, actually, what you can do is, so suppose V plus for the contradiction purpose, assume that V plus is not connected. Okay, so this is plus. Assume that V plus is actually disconnected. Okay, so we will prove it using contradiction. Disconnected subgraph. Okay, induce, or maybe induce. Okay, great. So let us, by default, let us choose that out of V plus. Okay, so there are vertices. Suppose you can write from 1 to up to S, right? So these are forming one connected component, and then there are the vertices S plus. So maybe write it this smaller one, S plus 1 up to R here. So basically your V plus is actually this. Okay, so let me write V plus is equal to all the vertices from 1 to up to R. Okay, and out of this, these are suppose, so this is a connected component, okay, and this is actually a subgraph on rest of the vertices. Okay, so now a component in V plus, okay. So now let us see the structure of the Laplacian matrix. Okay, so it will be like something this. Okay, so Laplacian matrix can be written as, okay, as this L11. This may be corresponding to this component. Okay, then this component has not any edge with the rest of the graph in B plus, so I will write it 0. Okay, and then it will have connection with the rest of the vertices, or maybe this V minus. Okay, V minus is there. Okay, very good. So now similarly here you can write L22. This will be L23, and this will be L31, L32, and L33. Okay, now do what? Okay, so suppose you have a Fiedler vector X. Okay, now break this Fiedler vector in actually 3 parts, which will, the size will be actually corresponding to the size of L11, L22, and L3. So let me write it as X1, X2, okay, and X3 here. Okay, so these are actually the basically chunks I am taken from the Fiedler vector X. Okay, so this is, suppose this I call it X is Fiedler vector. Okay, Fiedler vector. Very good. Now you see that. Okay, so from here to here, so this constitute of what? V plus. Okay, and this you can just think about the remaining vertices. Okay, now that means what? So X3 will be what? So all the entries in X3 will be negative. Okay, all the 3 will be negative because all the zeros or plus are consumed in this part V plus. Okay, now what? So let us write the equation from here that this. So this will be what? L11 times X1, and then this is 0, okay, plus L13 times X3, okay. This is actually giving you what? This will be giving you, because this will be equal to mu times the same vector, right? Mu times the same vector, okay, because your algebraic connectivity is mu here, so this will be giving you this. Okay, so this is indeed equal to mu times X1. Okay, now what are the implications of it? If you see that this L13 is always less or equal to 0, right? Every entry is either 0 or minus 1. Okay, and you know that, and X3 is less than 0. So this implies what? This implies this, right? This implies, let me write in the next page. So this implies, maybe here I can write this. This implies that L13 times L cube is always greater or equal to 0. Okay, now the important thing is know that L1 has at least one non-zero entry. Why it is so? L13 has at least one non-zero entry. Why it is so? If you see that, because this graph is connected, so this chunk will have some basically, so this part must have one edge with this, right? Similarly this part, no need to take care of L22 right now. Okay, so you know that this component must have an edge with L13 because the graph is connected, right? The graph is connected. So as the graph is edge G is connected, as G is, maybe I write down here, connected. Okay, L3 has an non-zero entry. Okay, so that means this L13 is not equal to 0. Okay, very good. Okay, now how can we make use of these observations? So that from here, okay, so you can, first thing is this, you can immediately write that L11 minus mu, okay, times x1 is less or equal to 0. This is coming from this fact, okay. Now what? And also due to this fact that this L11 minus mu x1 is not equal to 0, okay, due to this. Very, very good, okay. These observations are super easy. Now how to make use of this to prove that V plus actually induces a connected subgraph, okay. What I need, okay. So up to the here the things are pretty much clear, okay. Now let us claim that, and by the way, suppose if you okay, so yeah, maybe if you do this this operation, what will be the quantity, what we can say about this number? Remember, x1 is always due to our definition is always non-negative, okay, and this part is again less or equal to 0. So this will again give you less or equal to 0, okay, due to this, okay, because x1 is what? This is non-negative vector, okay, and this is less or equal to 0, so that means this has to be less or equal to 0. Very good. Now we claim that, let us make one claim. Claim is this, okay, claim is this L11, so this this matrix L11 minus mu is, maybe I will write this, okay, so now mu is mu times identity matrix. In fact, I have to actually make here identity wherever, so sorry about this, identity matrix here, okay, so maybe above also, and yeah, very good. So this very is not a positive semi-definite matrix. So let us actually prove it, not a positive semi-definite matrix, okay. So maybe we are claiming that this is not equal to 0, okay. So it's not a positive semi-definite matrix. So suppose it's a positive semi-definite matrix, that means for every vector x, so suppose L11 minus mu is positive semi-definite. This implies then what will happen? Then we can write this, right? X1, so maybe actually I write this as 1 here. X1 transpose, oh sorry, this is transpose, I'm making some mistakes here, okay. So this will be transpose, x1 transpose times L11 yeah, minus mu identity matrix, and times again x1. This has to be greater or equal to 0, right? Because we have assumed that it's a positive semi-definite matrix, okay. This implies by this, so let me call 1, okay. So by 1, this implies that basically x1 transpose, okay, times L11 minus mu times identity matrix. This will give you yeah, x1 equal to 0, okay. This will be equal to 0. But remember, if it is 0 and L1 mu I is positive semi-definite matrix, we have just proven one lemma. In that case what will happen? So let me go to the lemma, okay. In that case what will happen? In that case we will prove that this bx actually we have proven that this bx is equal to 0, right? So that implies here is this. Let me scroll it a bit faster, okay. So this implies that, so this further implies that L11 minus mu times identity matrix times x1 is indeed 0, which is a contradiction due to this, okay. So let me call it now 2. I'm doing the reverse side, reverse direction, but anyway, so using 2, this is a contradiction, okay. So by 2 it is a contradiction, okay, okay. This implies that L1 minus is not a positive semi-definite matrix. This is not a positive semi-definite matrix. This implies further that there will be at least one eigenvalue negative, okay. That in fact that means that, and this further means that an eigenvalue of L11, okay, is less than mu. Okay, and now the similar thing we can say about L22. Similarly, okay, similarly, the an eigenvalue. Similarly, let me write with my smaller a. Okay, so an eigenvalue of L22 is less than okay, so less than mu. Okay, so that means what? If you talk about this matrix L11 0 0, remember this is a principal submatrix, right? Principal submatrix of bigger L. Okay, so there will be the second smallest eigenvalue. So this implies that so suppose the second smallest eigenvalue of this matrix is mu dash. Okay, so let the second smallest eigenvalue of this matrix is mu dash. Okay, so that means what? This mu will be so mu dash will be always less than this, right? Because it has an eigenvalue which is less than mu. Okay, it has an eigenvalue which is less than mu. So the second smallest eigenvalue of basically this matrix is actually, so suppose this is mu dash, that is mu dash is less than mu. Okay, but by Cauchy-Intel's theorem, okay, remember this is a principal submatrix of L. Okay, so this is a principal by Cauchy interlace. Okay, interlace. We know that the second smallest eigenvalue of the larger matrix, okay, which is in fact must be less or equal to second smallest eigenvalue of this. So by interlace theorem, mu is actually less or equal to mu dash. Okay, which is again a contradiction. Okay, so which is a contradiction. Okay, hence we claim that, okay, our assumption was what? V plus H are disconnected. Okay, so this claim is wrong, hence V plus has to be connected. Hence V plus is giving an connected induced subgraph. Okay, and similarly we can say about V minus, and similarly it holds for V minus. Okay, so V plus is giving a connected induced subgraph, V minus is also giving an induced subgraph. This we can see just by looking at the structure of Fiedler eigenvector. Okay, we will see some examples in our tutorial session or in assignment. Okay, so I hope you enjoyed this lecture, the power of algebraic connectivity and the corresponding Fiedler vector. Okay, so I am stopping this lecture here. See you next time. Thank you very much.